Welcome to the Knowledge Graph seminar. Today, we are in the week 5 of the course, where our focus has been on how to create a knowledge graph from unstructured input. We have two outstanding speakers with us on this topic. Dr. Aditya Kalyanpur is currently with Elemental Cognition, and in his previous role at IBM Research, he helped create the computer program that beat humans at the game of Jeopardy! He is going to tell us about how he is using knowledge graphs for natural language understanding. Dr. Ranjay Krishna, he's a freshly minted PhD. He just defended his thesis last week. He has created many influential data sets in computer vision, including visual genome and action genome. He will be telling us about how he has been using scene graphs for understanding images. So Aditya, we'll start with you. So over to you.
Thank you so much, Vinay. Thanks for inviting me. I'm just going to share my screen. Okay, and there we go. Can you guys see the slides?
Yes.
Okay, so I'm going to talk about causal knowledge graphs for natural language understanding. And I'm a senior research scientist at Elemental Cognition, which is a AI startup that works in the natural language understanding space. So let me start by talking about a very popular problem in the NLP community. This is the narrative comprehension task. And a particular variant of it called the story close. And this is on the rock story dataset that came out in 2016. So I don't know how many of you are familiar with this, but the story close task is very simple. You're given a particular story, like a short story, and you're given two potential endings to this story. And the task is to pick what ending you think makes sense given the context of the story. So this is the task that requires common sense knowledge, because you have to understand what situation is happening in the story and then predict what you think is most likely to happen. And so in this particular example, Jim got his first credit card in college. He didn't have a job, so he bought everything on his card. After he graduated, he amounted a $10,000 debt. Jim realized that he was so foolish to spend so much money. So given the story, what do you think comes next? That Jim decided to devise a plan for repayment, or he decided to open another credit card? Most people, will pick this. This is the most likely plausible ending given the story. And humans do exceedingly well at this task. When they created this data set, they ensured that there wasn't any ambiguity in the two choices, and that 100% humans did 100% accuracy on this task. Like, they all agreed on what the correct ending was. Yet for machines, for an AI system, tackling this task was pretty challenging. When this came out, the accuracy was about 65%. And this is a simple multiple choice with two choices, so the random baseline is 50%, right? So there's a huge gap, at least when it came out, between the capabilities of AI systems and humans. This was back in 2016, and a lot has happened since then. So those of you who have been involved in the NLP community know this. Things got very interesting in late 2017 and early 2018. And one of the big things was a paper from Google Research, Attention is All You Need, which introduced a new kind of neural model called transformers. And these are, again, neural models for tackling sequences. And compared to earlier sequence-based models like recursive neural nets, RNNs, or LSTMs, the main distinguishing feature of transformers is they're non-recursive. So they attend to the entire sequence of text at or tokens in one shot. And because of that, they can learn much more efficiently. You can train them much more efficiently than the earlier models, which were sequential and recursive. And it has this whole feature around attention. It's property about around attention. So the idea is that all these neural models, what they're doing is they're learning embeddings for words or tokens. And that's how they're capturing the meaning of these tokens. And the idea is you're learning embeddings for a particular task. And I'll talk about what that task is in a second. But the key idea here was around attention was, when you learn an embedding for a token, you figure out how much attention to pay to nearby tokens in that sentence. So which totally makes sense. Like the way we assign word meanings is it totally depends on the context, right? You get the meaning from the neighboring words. And so what these models learn is, given a particular word in context, how much attention should I pay to neighboring words? And that's this attention-based function. And the task that you're training this for is a language modeling task. So your standard language modeling task is you're given a text sequence and you predict what comes next, what word comes next. And that's what this GPT-1 was trained on. There are other variants of this this one is called masked language modeling, where the idea is you're given a sequence and you mask some words, you take out some words, and you're asked to predict what those words are. Like it's like a fill in the blank task. And that's what BERT did. And so BERT and GPT-1 are systems that are based on the transformer architecture. They're trained for these language modeling tasks or mass language modeling tasks. And because this architecture is much more efficient at learning, they're trained on very, very large data sets on web-sized corpora. And that's what we mean by pre-trained transformer models. They're trained on these large web-sized corpuses for this LM task. And the cool thing they showed was that once you take these pre-trained transformer models, you then can fine-tune them on other NLP tasks you have, on downstream NLP tasks. And those tasks could be anything from question answering to common sense reasoning like the rock stories, to sentiment detection, to summarization, entailment, like pretty much any NLP task you have, as long as you have some training data, you can fine-tune these transformer-based models and achieve state-of-the-art results. And that's like the recipe that they showed worked very well for a whole bunch of NLP problems. And in particular, going back to the rock stories, using GPT-1, the accuracy for this particular model, GPT-1 fine-tuned on rock stories was 86. So already way better than just a year back. And since then, what's happened is, a full explosion in the various kinds of transformer models. Different companies, universities all have released, variants of these transformer models. And they all are based on the similar architecture, on the transformer architecture. They differ in a few interesting ways. One is what data set they are trained on, the pre-training data set, what the actual pre-training task is. Like they're all different variants of language models. Typically, like XLNet is something has a pre-training task called permutation language model. Anyway, and they have different architectures. Like they'll have different number of layers, different the size of the vector dimension, the vector embedding that's being learned, the dimension is different, and so on. But by and large, conceptually, they're all very related, and they all give excellent results on a variety of NLP benchmarks. But in spite of that, what has also happened is people are starting to think about, okay, fine, these do great on these data sets and they're achieving close to human level performance on a bunch of different NLP data sets. But what are some of their weaknesses? And what is the limits of this? And in particular, there are two main problems that most people have found. One is that they're essentially black boxes. It's hard to debug what's going on. It's hard to explain a prediction. And there is interesting research that's happening on kind of going under the hood and visualizing like the attention map and stuff, but it's still a long ways from getting a logical explanation. That's not what these models. That's not how these models work. And many a times when you start debugging them, you realize that they're getting the answer right, but for a very wrong reason. Like it doesn't really make sense. It seems like it's picked up some quirk in the training data and some kind of pattern in the training data. And as long as the test distribution is similar, it works great. But the moment you go across domains, like you have a question answering system that is trained on Wikipedia data and you try to apply it to like children's stories, they do very badly, right? So they're not really understanding language the way humans do, because if humans could, understand complex concepts, in Wikipedia, that level of language and semantic complexity, they should be able to do well on children's stories, right? But that's not how these things work at all. And certainly across tasks, they are even more, they don't work well at all. Like if you have a QA system and you try to apply it for sentiment detection, like it doesn't really do well. And so this is one of the papers that we published at EC, is we questioned whether the benchmarks are even the right ones, that are we even testing the right metrics? And so we defined for language comprehension, we defined a more challenging set of metrics for that somehow that demonstrate deeper understanding of stories. And we found that all these state-of-the-art transformer-based models really did very poorly at them. And so our goal at EC is we want to go beyond these sort of, I would say, shallow text understanding systems and build a system that can read, reason, and understand text by building explicit, this is the key point, explicit logical conceptual models of the meaning behind text. So just as humans do when we read something, we build a mental model. We're mapping it to our sort of internal model of the world, and we're continuously updating that as we read text. And so having that rich underlying internal structure is something that we believe is needed to explain how you came up with something. And we also see this as a collaborative process. Like this is something that the AI and the human work together to achieve this shared understanding. That's how all communication works, between people as well. So that's what we're shooting for. And so coming back to this rock story closed test problem, let's again look at this another example from the rock stories, and let's just think at what do humans do when we read these stories, right? So here's a rock story. Actually, we changed the name in the story. We made it a Peppa Pig just for fun. The original story had a different character name, but let's say this is your story. Peppa was riding a bike. A car turned in front of her. She turned her bike sharply. She fell off her bike and she skinned her knee, right? So as you're reading the story, what happens in your mind is, you're building a rich representation of this scene, and you're pulling in information from your background knowledge to enrich this scene. And you're constantly asking yourself, like, what is happening in the story? What are the main characters? What things are they doing? What are their motivations? Why do things happen? And that rich understanding is what these neural models are kind of missing, like capturing that explicitly. So for example, things that we can do very subconsciously, and we do it really well, is we can form a causal chain of events in the story. The fact that a car turned in front of Peppa is probably what caused her to turn her bike sharply, which probably caused her to fall off a bike, and that caused her to skin her knee, and that probably led to her asking for help, right? That's an inference that doesn't even exist in the story, but we can deduce that from, based on common sense knowledge, right? And yet another thing we could do is track characters' emotions and states throughout the story. That Peppa was initially on the bike before she fell. Then after that, she was on the ground. So we're tracking location information as well. And then emotion, like I said, like you don't know how she was before, but she probably wasn't pain or upset after she fell, right? And so we humans are pretty good at building these rich mental models of situations from when we read or process information, but AI systems do very poorly at this. And why is that? And there's two main reasons. One is they just lack this common sense knowledge, and we don't have any efficient ways to even acquire this common sense knowledge at scale. And most of this is very implicit stuff. It's not information that you'll find written in a corpus. And that's one of the main problems we have. Like if we have neural models being trained on written text, but this information is implicit, the signal is not even there for these models to learn. And the second problem is, let's say you even have some magical way to acquire all this common sense knowledge. You have this problem of how do you efficiently bring that knowledge into a reasoning system? How do you figure out which subset of that vast common sense knowledge is relevant for understanding a particular situation? So there's that efficiency, scalability problem as well, from a reasoning standpoint. So to tackle this is work we did. We came up with this data set called Glucose, Generalized and Contextualized Story Explanations. This is a paper that was published last year at EMNLP. It won honorable mention for best paper. And the goal was to tackle both these problems at scale. And it was a big group effort from all of us at EC. Nazrin was the lead author on that. So what do we do here with the glucose for glucose? So the idea here is we said, let's define the following problem. You have a story, S. You have a particular sentence in that story, which typically maps to one event in that story, X. And we want to capture causal explanations, common sense causal explanations along 10 different dimensions related to X. So the first 5 dimensions are as follows, like what events directly cause X? So that's like the causal relation directly. What emotions or basic human drives motivate X? So we're going at human motivation information, knowledge. What location, or this is spatial information. What location states enable X? What possessions enable X? And are there any other attributes of entities involved in X that make it possible, like needs and requirements and so on? And these are the first 5 dimensions. And the 6 to 10 are just duals of these 5. So, for example, dimension 1 is what events cause X, and dimension 6 is what is caused by X. So you could think of 1 to 5, these dimensions, as being temporally happening before the event, and 6 to 10 are temporally after. And we came up with these dimensions, by reading about cognitive psychology literature, and also by, and as I'll talk about this, by talking to users and figuring out, because we wanted to acquire this knowledge, we wanted to come up with dimensions that lay users can easily relate to. So it can't be too confusing. And this is why we combined causes and enables, because initially we had those as 2 separate relations, but that seemed to confuse a lot of users. So we just combined them. So here's an example of collecting glucose data, these causal rules, again, going back to the pepper story. So this is our story, the 5-sentence story. And here's the sentence in focus that we want to collect information about. And we want to collect these causal rules. And there's some structure to them. So a rule has an antecedent and a consequent. And the dimension is what's connecting the two. But also we're collecting, when we say semi-structured, we're collecting the antecedent and the consequent using very simple syntactic templates like subject, verb, prepositional phrases, or subject, verb, object. And so in this particular case, for dimension 1, the question is, what event caused Peppa to turn her bike? And someone might say, well, the car turned in front of her is what caused her to turn her bike. And so this is like a very simple, semi-structured, because you have this syntactic information here, causal rule for this dimension in the context of this story. So this contextualized and very specific rule. At the same time, we're also collecting general rules. So we want to go beyond the specific entities in this particular rule, like car and Peppa and bike. And we want something slightly more general, like if something turns in front of something that's a vehicle, then maybe that causes someone to turn away from it. And again, these rules don't have to be perfect. They're highly contextualized, and a slightly better general rule is for the second dimension, where if someone wants safety, that might enable them to move away from something that is dangerous. And so we collect these specific and general rules along these different dimensions. Here's an interesting one. If someone is close to something, that enables someone to move away from something. So this is something that's so implicit. You're not going to find this in a corpus, right? People don't write stuff like this. Like in order to move away from something, you need to be close to it. And we're talking about physically move, and so there's sense information here as well. And then the remaining dimensions. In this case, what possession information enabled this? Well, the fact that she possessed a bike allowed her to turn it. You need to possess it before you turn an object, before you do an action on an object. And in this particular case, the 5th dimension wasn't applicable. And so the point here is, if you step back and think about what we're doing, what glucose is capturing these mini causal theories about a given story and events that happen in that story, where these causal theories are tracking states, motivations, and so on, inspired by human psychology. And if we can collect this at scale, now you have a library of these mini causal theories, which maybe you can do some interesting common sense reasoning with. So now the question is, okay, we've defined this problem, and it would be nice to collect data as we've defined it, these specific as well as general rules that are grounded in a particular context. The question is, how do we collect this data at scale? And so what we did is we came up with a very effective multi-stage crowdsourcing platform. We deployed this on Mechanical Turk, and we did, I think, about 6 rounds of pilot studies to come up with a UI that is very accessible to crowd Turkers. And the 3 main steps. The first is we had a qualification UI. So here we had the same task. We gave them a story and a sentence highlighted, and we asked them these causal explanations, except here it was multiple choice. So we didn't have this open-ended, because we had to make sure that we knew what the correct answer was. So this is like a qualification test. And only if they did better than 90% on this qualification test what they even selected for the main task. And so this is the main task where you actually are collecting, open-ended explanations. Again, same problem, story, question, and then you have 10 different dimensions that we're collecting these specific as well as general rules on. And finally, after we collected that, we had a review dashboard. So we had our own reviewer. One of our EC internal folks was a reviewer who would rate each of these submissions on a scale of 0 to 3 and give feedback to the Turkers as well, which they would use to get better. And so through this process of crowdsourcing and running experiments, we had like a dedicated pool of expert Turkers who were very well versed with this task, and it could give us very high quality annotations for this task. And here's some examples of stuff we got, like data we collected. Someone gives someone something, it results in someone possessing it. Again, very basic, implicit knowledge. Here's some other examples. If someone is careless, then they forget something. If you forget something, it probably results in something being left somewhere. If you're tired, you might feel sleepy, and so on. And we collected around 620,000 inference rules over 4,700 stories, and 372 participants. And again, they spent less than 5 minutes on average per task, which is not bad given how cognitively challenging the task is. And to our knowledge, like this is one of the few really cognitively challenging tasks that has been crowdsourced at this scale. Well, and then the other thing we did once we collected this data is we said, okay, and we want to make sure, we want to compare it to other existing common sense knowledge bases, and the two that that are available openly. One is ConceptNet, and the other one is Atomic. And in the paper, we have details of exactly how we measured this overlap. We mapped relations. We mapped the 10 glucose dimensions to relations in ConceptNet and Atomic, and then we had a very lenient fuzzy text matching function to find similar instances of those relations or rules. And in spite of that, we found that there was very little overlap. Like glucose really captured a lot of new information that wasn't there in these sources. So, okay, we've collected the data, but now how do we incorporate this data, this knowledge into a state-of-the-art system, AI system? And the view here is we don't want just a static knowledge base of rules. We wanted something more dynamic. And so what we did was we said, let's use the neural models, the transformer-based models, and let's frame this as a machine learning problem, which is given a story and a sentence, and at one of these 10 dimensions, predict both the specific and the general rules. So that was a task we set up. And for the test set, we created a doubly vetted test set based on unseen stories, which we took the top 3 annotators that we have, the cloud Turkers, and only if they had very high agreement did we include this in the test set. And so as a result of this careful design, this test set had around 500 glucose story sentence pairs, and each of them had between 1 to 5 dimensions answered. And note that not all dimensions have to be answered. Like some of them is just not applicable in the context of the story. And we had 2 different evaluation metrics. One is automatic. We use BLUE or Seeker BLUE, this function for just text similarity. But because there's so much variance in this task, you can always produce a rule that means the same thing but uses different words. In the end, we said we'll have to have a human evaluation as well. And so for that, we had 3 human experts rate the results of the model. And then we took the average of the 3. And then, so for the human evaluation, we gave them a UI for this. And like I said, we collected ratings on a 0 to 3 Likert scale. So where 0 is completely incorrect, the rule is really bad. Almost incorrect is 1, almost correct is 2, and completely correct is 3. So now for the results. So we had 2 baselines, a KNN model, K nearest neighbor model. So in this model, basically you have your train set is just stored in memory or in a database. And then at test time, given a story and a sentence and a dimension, you find you have a similarity function that finds the most similar stories and events in that story for that dimension. And then you predict whatever rule exists in the train set. And this only makes sense for the general rules. It doesn't make sense for the specific rules based on the approach. And it did really poorly. So, zero point 0.5 out of 3. And again, these scores are three human annotators, the best annotators that we had based on our ratings of Turkers, and then the average of the three ratings. The GPT-2 model is your standard baseline here. So you take a language model like GPT-2, and we gave it as input the story, and we repeated the sentence, and then we added some trigger words for the relation. So if it's a causal relation, you might add a word like a filler word, like a phrase like as a result of or because of, and so on. And then we prompted the model to fill in the rest, right, to predict the rest of the rule. And again, we did this only for specific rules. So this is the opposite. For this, general rules didn't make sense because GPT-2 wasn't trained on rules that had things like some person X and person Y. So to be fair to GPT-2, we only evaluated it for specific rules, and yet it did pretty poorly. And so then the train model, so this is now taking GPT-2, the full LM is taking GPT-2 and now tuning it for the glucose task. So fine tuning it on glucose training data. And this model did much better. And an even better variant was actually, instead of using a language modeling architecture, we used an encoder decoder architecture. So we use the T5 model from Google. And we believe, and our hypothesis is this is just a much better fit for this problem. Because here you have, in this architecture, you have a clear separation of input sequence and output sequence. And here the input is, your context, your story, your sentence, and your dimension. And the output is the rule, either the specific rule or the general rule. And we had two separate models there. And here the results were really good. And actually, on this particular test set, this is still little data, it was pretty close to human performance. And obviously this is a small test set. It's doubly vetted, so it's very clean test set. But still, it was surprising to see that these models can work really well, even on this very challenging task of producing common sense rules on the fly. And this is on unseen stories, right? The test set had no overlap with the training. And so the conclusions are, the KNN model performs the worst, which kind of makes sense. It highlights the importance of generalizing beyond your training set. This is also not too surprising because how these models are trained. The pre-trained language models, so just out of the box, GPT-2, and we even tried T5. They just work very poorly at this task. And they don't, it's because they lack this common sense knowledge that is very implicit and not mentioned in corpora. But when you take one of these pre-trained models and you fine-tune it on high quality common sense rules, then even for this extremely challenging task of common sense reasoning, you still get pretty good results on unseen data. So that was a nice result. So some example predictions made using the various models. So here's a story. This is actually a rock story. Karen made a pan of lasagna. She brought it to the party. Nobody wanted to eat lasagna. Karen ate it for a week. She became tired of lasagna. Not the most interesting story, but so in terms of predictions, we are, remember the dimension here is 3. So what location enabled X? And X is this first sentence in the story. So one model returned, she was in front of a TV enabled Karen made a pan of lasagna. Can you guess which one this is? This is GPT-2, which makes sense in this, if you given how these models are trained, like, yeah, it's highly correlated. I'm sure there are texts that mention, making food or eating food next to a TV, but it's not really the right causal reason it doesn't enable her to cook. The language model, the full LM, which is basically GPT-2 trained on the glucose data, did much better. So Karen is at home, enables her to make a pan of lasagna. The encoder decoder really got the right one in this case. She's in the kitchen, and that's what the human said as well, right? If you're in the, that's what enables you to make food, is being in the kitchen. That's the location that enables this. Another example is dimension 6. So what does this cause? What is an after effect of this? And the encoder decoder model is not too far off. Like, she made a pan of lasagna is probably what enabled her to eat it for a week. That's in the story. And the general rule is slightly better. If you make food, it enables you to eat it. And the humans was, slightly better here. Someone prepares something is what enabled her to take it to an event. Here's another story. This is actually a kindergarten story. This is not from Rock, but just to give you an example of the kinds of knowledge that you can get from these models. Tom was hungry in class. He got an apple from his backpack. He ate some of it. It didn't taste good, and so on. And the sentence here in focus is he got an apple from his backpack. And if you run our best model, the encoder decoder model, on this trained on the glucose data, if you now apply it here, and this is not a rock story, this is a different story, you get predictions like this. So before, for dimensions 1 to 4, Tom was hungry in class. That probably is what caused him to get an apple. He was feeling hungry. That's the feeling. He's near his backpack is what allowed him to get the apple from the backpack. And he had to possess the backpack in order to get it. And then afterwards, he eats some of it, because that's why he got it. He wanted to eat it. Probably feels happy. The location is probably in the school. And now he possesses the apple because, he got it from his backpack. So again, very basic common sense, implicit stuff, but it's good that you have a model that can produce this on the fly on a story that's not even from the same distribution as the train, which was the rock stories. Okay, so this is the hypothesis that we verified. How am I doing on time? Almost done. Okay, which is that a promising recipe to give machines common sense knowledge is to first collect high quality knowledge from the crowd, and we show that there are ways to do that, and then use that as seed data to fine tune neural models. And so the novelty is not in fine tuning. That's what everyone else does. It's just it's the fact that we show that even for a task as open-ended with as much variance as common sense reasoning and producing common sense rules in context, you can get these neural models to do really well if you collect high quality data and fine tune it. And the interesting perspective here is this change in view from a knowledge representation and reasoning perspective. So my initial background is actually in formal logics, and I moved to NLP. But back in the formal logic space, you have a very static view of your knowledge base. Your knowledge base is a fixed set of rules that you have to encode beforehand, and you give it to your reasoning engine. And here we have a very different view. You have a dynamic knowledge base. You have a function or a model that can generate rules dynamically for you. And the question is, can you plug that into a reasoning engine? So that's the last part here, which is to show you the full piece. Okay, we have this a model that can generate rules for you on the fly, and both specific as well as general rules for you. And the question is, how do you use it? Well, at EC, we've built our own neurosymbolic reasoner called Braid. And Braid, it has foundations in logic programming, Prolog, and answer set programming, ASP, those of you know. And the main distinguishing features of Braid are just like all other logical reasoning system, it can give you a proof or an explanation for your answer. And it can rank those explanations on various metrics, like how plausible is it. And one of the key distinguishing features is this, the integration of statistical functions into the symbolic reasoner for doing things like unification or matching. So we can do basically fuzzy or weak unification. And relevant to this talk, it has a way by which you can insert rules dynamically. So dynamic rule generation, it has support for that. And there are lots of other features. It has a forward and backward chainer, constraint solver, and so on. And there are details in this paper if you want to know more about it. But the key point for this talk is that as the reasoner is searching for an answer and it's exploring its proof space, its search space, it's doing that by consulting a static knowledge base of rules, which is how most reasoners work, but also by consulting a dynamic rule generation model, where we can plug in like this model that was trained on glucose data, and now it will generate rules for you during the reasoning process to fill in the gaps. And so here's an example of where we use this. This is another kindergarten story. Fernando goes to a plant sale. He likes the minty smell of leaves. He bought a plant and placed it near a window. And the question is, why did Fernando buy a mint plant? And it's a very straightforward question, but yet a lot of the state-of-the-art QA systems, like the squad system, when we tried for this question, it did really badly. And so these are the facts that we've extracted from the story. And that's done using our NLP system that we have. We have a state-of-the-art semantic parsing system at EC. So that pulls out these facts. But there's a big gap between these explicit facts in the story and the top level goal is what motivated Fernando to buy a plant. And the way we connect the dots is we have rules, and some of these rules are manually encoded, but extremely general, highly fundamental rules that work across all domains. So we call these core theory rules. Like if an object has a part and that part has an attribute, then maybe the object has an attribute. So in this case, plants have leaves, and in this case, the plant has leaves, and the leaves have a minty smell. So you might deduce that the plants have a minty smell. And then we get this rule from the dynamic rules generation model. So this comes from the model trained on glucose data that if an agent likes the property of something, they might like the thing itself. Again, a very implicit rule. So in this particular case, the plants have a minty smell, and Fernando likes the minty smell of leaves, so maybe that's why he likes the plant. And finally, yet another dynamically generated rule that completes the full chain is if a person likes something, then they're motivated to buy it. And so maybe we know that he bought the plant, the story says so. And so we could abduce that maybe that's why he, and he likes the plant, and maybe that's what motivated him to buy it. And so we come up with this rich explanation for this answer, which we can, which we can provide, unlike a end-to-end deep learning system. And these rules don't have to be encoded beforehand. And even this rule, even though it was encoded, like I said, it's extremely general. It works across most domains, but we could consider acquiring rules for this kind of knowledge in glucose as well. It just so happens that this is not one of the dimensions that we have right now in glucose. But you can see the potential of technology like this is you can really go beyond having static knowledge bases and plug in a statistical rule generation function in a symbolic reasoner. And just finally, last slide.
Aditya, we've just got a couple of minutes.
Okay, so I'm going to skip this just as results in the paper. And just to go back on the rock stories, we use Braid with a dynamic rule generation model, and we got close to state-of-the-art performance. So now, remember I told you 65% 4 years back, now it's already in the 90s, it's 90. We're very close, but the difference is, unlike these other black box-based DL solutions, we can give you a frame-based explanation as well. And the details are in a paper. And so to conclude, we basically show three things. One, it's possible to collect high quality common sense and causal knowledge from crowd workers if you design the appropriate models, the formalisms, the tools, and the UIs. Second, an interesting recipe to doing dynamic rule generation is to collect this semi-structured inference rules and then fine-tune your model. And now you have a KB that is no longer a static rule KB. You have a dynamic rule model. And lastly, you can take these dynamically generated rules and plug them in a neurosymbolic reasoner to do question answering. And these now you're addressing both the drawbacks of both traditional KR systems, where you have the problem of they're very precise, they're brittle. You have the knowledge acquisition problem, where you're going to get the rules from. And the well-known drawbacks of end-to-end models is you can't explain yourself. Like, what is the logical explanation for how you came up with the answer? And so this kind of addresses both those. That's it. Thank you.
Excellent presentation, Aditya. So without further delay, let's move on with Ranjay's presentation so that we still have time at the end for questions. Ranjay, please, over to you.
Sure. Give me 1 second. Okay, just checking in that everyone can see my slides.
Yep, looks good.
Okay, great. So thank you for having me. I'm here to tell you about how we can design computer vision models using knowledge graph-like representations. So although computer vision has gotten really good at identifying objects, and you must have heard all about all the improvements through ImageNet, our world is more than just a collection of these objects. And our world is rich, it's vibrant, and people are constantly surprising us with new kinds of performances. They repurpose items for new use cases, they find themselves in predicaments they never thought they would, and they even start using equipment in ways that we have never seen, and in a manner that we might have never imagined. And even animals surprise us with their fashion sense, as well as their unexpected agency. Now, these sort of new situations that we encounter in the world, they're commonplace. We can interpret and reason over these with very relative ease without any problem at all. However, despite a decade of amazing advancements, the deep learning models that are powering the vision technologies today, they really struggle to understand the visual world. And prior work has noted many times that vision models struggle to generalize when they see novel compositions of concepts that individually they might have already seen. For example, even if they've seen examples of fire hydrants and people, these models, they end up learning how to cheat and ignore entire regions of the image when making predictions. They end up predicting that a person here, for example, is sitting on a chair instead of sitting on a fire hydrant. And they make these mistakes because they inherit biases in the data, because most instances of people sitting are sitting on a chair. In fact, even the latest sort of 12 billion parameter models that were released by OpenAI earlier in January, these ones that you end up using over 400 million training data points, these models still fail to generalize to these novel compositions. So this entire problem is more of a representation problem and not necessarily just a data problem. Now, we know in contrast that human cognition can construct an infinite number of representations from just a finite set of previously seen concepts. Humans inductively develop this compositional model of the world using their past experiences, and this allows us to sort of appreciate new situations and learn new tasks really quickly. So enabling this human-like visual intelligence is a challenging problem, and it'll require us to fundamentally modify computer vision's predominant reliance on using just object representations for most tasks. So inspired by human learning, I'm going to tell you today about how some of my research is trying to move away from just thinking about objects and developing visual intelligence or computer vision models using ideas from human cognition. Now, my main goal here will be to show you that we can move agents to generalize to novel compositions that are completely absent in their training data. So in today's talk, I'll explore how we can design these models to generalize to novel compositions. I'll begin by drawing on Biederman's scene perception model and Jeremy Wolf's model of visual memory in cognitive science to design a new visual representation. And then I'll show you that with the right representation, my research now makes it possible for models to learn from a finite set of situations that are outlined in their training data and allows these models to generalize and recognize completely new situations as a composition of these previously seen concepts. So today, I will first introduce scene graphs, which are this dense, compositional, general-purpose visual intelligence representation. And then using scene graphs, I'll design models that are better at recognizing novel compositions. And then finally, we'll use these scene graphs to enable a whole host of downstream computer vision tasks with as few as 5 training examples. Okay, so let's get started. So the predominant paradigm for training computer vision models today is pre-training these large latent representations on large amounts of web scrape data or pre-training object representations on large data sets like ImageNet. And then later on, adapting these learned representations for any sort of downstream task that you might want, like image captioning or visual question answering or what have you. Now, unfortunately, these latent or object representations often struggle to generalize. They, like I said, learn these shortcuts and ignore entire regions of the visual input if they could get away with maximizing performance on the dataset. And because these learned representations end up becoming incomplete, the downstream models that end up using these representations need a lot more data to achieve any sort of reasonable performance. So our main insight is going to be this new representation, which we're going to call scene graphs. And I'll show that pre-trained models on scene graphs will help models generalize to completely novel compositions, like a person sitting on a fire hydrant, for example. And because this representation captures more information in a compositional manner, the downstream models will need much fewer training examples in order to get any reasonable performance. Okay, so first let's get started with thinking about how we designed the scene graph representation. So let me contextualize first why object representations, which are the most common form of pre-training in computer vision, is insufficient for a wide variety of downstream tasks. Now let's look at these two images. The object features or object detection will tell you that there are 2 people in these images, and it'll even tell you where they are. Now, knowing this information would likely make us believe that these 2 images probably contain similar semantic content. But sometimes these same sort of object detection features might have very different interpretations. For example, in one image, we've got a person angry and yelling at another, and in the other image, we just have a person paying attention to someone else. So when we use these object representations for downstream tasks, it's really no wonder that these models have such a hard time generalizing and why they need so much more data to enable tasks like captioning. But that leads us to a follow-up question. What is a good visual representation? Now, we know from human vision that people are really adept at generalizing to novel compositions. So in an effort to establish a representation for visual intelligence, we turn to computational neuroscience and psychology, hoping to find inspiration for how people process visual stimuli. Now, back in the 80s, Irving Biederman, and later again in the 90s, Jeremy Wolff, they were exploring this very question. And of course, by no means were they the only ones exploring this question. Biederman concluded from his experiments that aside from categorizing objects and scenes, people were simultaneously processing attributes, and which are properties of objects, as well as simultaneously processing relationships between those objects. And these relationships are like the interactions that people have with objects around them. Now, attribute violations like the person in the first image being transparent, or relationship violations like the fire hydrant on top of the mailbox, these violations slowed down his test subject's ability to categorize the objects. And he concluded from his experiments that this slowdown in object processing probably implies that we're processing attributes and relationships in parallel to objects, thereby interfering with our ability to understand which objects are present in the image. And a similar set of experiments in human memory, again from Jeremy Wolff, also concluded that objects are insufficient to explain the human visual representation. And he also said something very similar, that we must be encoding these relationships or interactions between these objects in parallel to object identification. Now, noticing this grounding in human cognition across multiple studies, across multiple decades, we designed a new visual representation, which we called the scene graph. And the scene graph representation encodes every single image as a set of objects that are grounded as bounding boxes. Each of these boxes are associated with attributes for every single object, which are describing different sort of characteristics about these objects. And they're also connected to one another using relationships. And this is just a small graph that explains a small portion of the image. And to truly study the effects of scene graphs, we embarked on a project called the Visual Genome Project, which aimed to map out the visual world with scene graphs. And here's a real scene graph from the Visual Genome Project. We ended up annotating quite a large data set to study the utility of using scene graphs for a wide variety of computer vision tasks. Okay, so with scene graphs designed and a data set collected, we began training models to predict scene graphs, and we're pretty excited when we found evidence that these scene graphs are in fact better at generalizing to novel compositions. However, training these models to predict these scene graphs was quite a difficult challenge. So let me explain what that challenge is. So formally, we can train scene graph models to expect an image as input and generate a graph structure with objects detected within the image, with attributes associated with every single object, and relationships between pairs of objects. Now, for the rest of my talk, I'll ignore attributes because they can be modeled very similarly to objects. I'll instead focus just on the structured prediction task between objects and relationships. So here we would want to detect the person, the hat, the field, the horse, as the different kinds of objects in the image. And we want to be able to classify the relationships between pairs of objects. For example, we might want to be able to say that the relationship between the person and the horse is standing on because the person is standing on the horse. Now, what makes scene graph prediction so difficult is its long tail distribution of relationships between even a single pair of objects. Now, there are dozen ways in which a person can be interacting with a horse, and some interactions like riding a horse are just far more common than ones like standing on a horse. So treating each combination of these two objects and their relationship as a separate category results in this quadratic increase in the number of possible categories. More precisely, if we had n object categories and k relationship types, we would need to build n squared times k number of output categories. And because most of these combinations only have a few training examples, these models end up predicting the most common combination, which is person riding a horse, and ignoring the ones that are less frequent, like person standing on a horse. So to prevent this sort of overfitting, we decomposed the problem. Instead of predicting the objects and relationships together, we predicted the objects independent of the relationships. And so these relationships were now being predicted directly from the image features, not predicted in conjunction with the objects. Now, our decomposition is a consequence of Biederman's conclusions that the human vision visual processing processes relationships in parallel to objects. And similarly, our model now also processes relationships independent of the objects using a separate branch. Now, aside from the cognitive grounding, this decomposition also alleviates our long tail problem, because even if a person is standing on a horse, it occurs very infrequently in our data set, the object detectors will have seen enough examples of people and seen enough examples of horses in various different contexts where they can understand and identify these objects. And similarly, the relationship detector will have seen enough examples of things standing on other things so that it can also predict the right relationship appropriately. And once these relationships and objects are predicted independently, we can combine these individual predictions using a cross product by making a naive Bayes assumption to produce this sort of n squared times k number of predictions. But now we only need n plus k number of categories to train our model. So with this new formulation, the decomposition of the visual processing into its separate object and relationship branches, this now allows our models to generalize to completely novel compositions of concepts that they might have seen individually. So for example, by looking at examples of people riding horses and people wearing hats, we can now take these individual pieces together, and our model can now generalize and predict when a horse is wearing a hat. And this is an example of a composition that was completely absent in its training data. And similarly, of course, going back to the example we started with, by looking at examples of people sitting on chairs and fire hydrants on the ground, we can now, again, take these individual pieces from these other training examples and then combine them to predict when a person is sitting on a fire hydrant. Again, an example that is completely missing from its training data, but one that our model can now predict. And our model was able to improve mean average precision over detecting objects and relationships by about 3x as compared to a variant that was trained using object features to learn relationships. And while this result was encouraging, we wanted to see if we could push this performance further. So we began analyzing what were the common sources of error. And we found one type of error that kept on appearing. So let's consider this image. So our model looks at this image and predicts that both people are throwing the frisbee. It doesn't have any sort of higher order reasoning capability that rationalizes that if one person is throwing a frisbee, then a second person can't possibly be throwing the same frisbee. Instead, the second person must be trying to catch the frisbee or reach for the frisbee or something else. And this error occurs because the relationship prediction is done in a feed-forward manner, and the model doesn't really reevaluate each prediction by placing it in context with all of the other predictions that it's trying to make. Now, in contrast, again, we know from human vision that our processing is abundant with feedback connections where we share information and correct these sort of incorrect predictions and making a more holistic, coherent prediction. So similarly, can we improve these models using a similar mechanism? And we began exploring ways in which we could do that. And we developed a method for doing this sort of higher order level of reasoning. And to do that, we extended our original model with a new graph convolutional layer. In our work, we extended the traditional graph convolution formulation to operate over 3-dimensional visual representations and over 2 special kinds of nodes, object nodes and relationship nodes. Now, object nodes, they learn a function that we parameterize using a small convolutional neural network to pass messages from the relationships that it's attached to. And similarly, the relationship nodes are also learning to incorporate information from the 2 object nodes that it's connected to. And by iteratively updating both the object nodes and relationship nodes over multiple iterations, we can effectively pass information across the entire graph. And finally, when our model does make a prediction from these individual nodes and relationships, it can now have all of its necessary information to make the correct prediction that the second person is not also throwing the frisbee. And with graph convolutions, we were able to add another 5 mean average precision points to our performance. Now, aside from the quantitative improvements, modeling these relationships as these sort of functions that transform representations for objects and relationships, this also allows us to develop contextual object representations as well. Just like contextual word representations in natural language processing have become really, really popular, and just like you could do arithmetic operations on those word representations, we can now perform the same kinds of representations using our contextualized object representations. And unlike word representations where the transformations can be arithmetic, our operations are defined by transformations that relationships perform on these objects. For example, we can now apply the eating transformation, a relationship on the people cluster, and by applying that transformation, we now arrive at the food category location where items like pizza and ice cream and noodles coexist together. And you might also see that on the top left, there's a cluster of things that afford writing. And unlike semantic encodings that would put horses and skis far apart, but because both of these types of objects afford the same kinds of relationships, namely writing, they're now closer together in some dimension that allows us to use the writing transformation and arrive at these sort of affordance-based representations. And what's nice about having this sort of contextualized object representation is that we can now train models to recognize new relationships and new objects with very few training examples. For example, with just one example of the relationship picking up from an image of a person picking up a burger, this model can now learn that women and children can also pick up other food items because it learns that burgers are things that can be picked up, so therefore other food items can also be picked up. And because a man can pick it up, a woman and a child can also pick it up. So it's learning to make these associations because of this contextualized representation that's built out. Now, graph convolutions are, of course, just one of the many potential frameworks that we can use to produce this sort of higher order reasoning over relationships within an image. And the computer vision community has been building upon our original framework to develop hundreds of scene graph generation models. And these methods incorporate many ideas from numerous fields, ranging from message passing to reinforcement learning to recently a lot of transformer-based models. But across all of them, one thing has remained pretty consistent, and that's the original decomposition that we introduced that was inspired by Biedermann's work. The only thing that's really changed across all of these hundreds of models is how we design these feedback connections. Like I mentioned, people have been using all of these different kinds of newer methods to design these feedback type of connections. So finally, let me sort of touch upon how we can utilize these scene graphs that we can now predict from images and generalize to novel compositions. How can we use these to enable a whole host of core computer vision tasks? So downstream tasks, for example, like action detection, are extremely data hungry. We found, for example, that it's really difficult for these models to find any meaningful signal in videos because these videos can have hundreds of frames, and it's really difficult to find the right signal to make any sort of right prediction about what action is actually taking place. But if you have a scene graph model, what you can do instead is now represent each of these frames as a scene graph. And now you can study action detection or action recognition as a transformation of relationships between objects across these different frames. For example, our model can learn that the action waking up in bed results from a change in relationship between the person and their bed. Initially, the person is lying on the bed to later on sitting on it, implying that they're now performing the action waking up. And if you have this sort of data now to create these representations, what we've shown recently is that you can use as few as 5 to 10 training examples and increase the mean average precision for action detection by pre-training on scene graph models and only needing 5 to 10 examples of each object that you want to detect, and improve performance from pre-trained models by about 5 mean average precision points. Now, aside from action detection, we've also been utilizing scene graphs as an intermediate representation that connects language and vision together. And this allows us to decompose a variety of different language vision tasks by inducing a sort of graphical representation in between. For example, we showed very early on when we were playing around with scene graphs that we can improve image retrieval by first decomposing these long queries of things that you might be looking for into a scene graph, and then later on using that scene graph and matching it to the scene graphs extracted from images. So doing this graph matching process allows us to retrieve images that are likely what you're looking for, that is the best match for the kinds of language descriptions that you're providing as queries. And other people in the vision community has also similarly been using scene graphs to improve a wide variety of other tasks. For example, image captioning. There's a variety of different models that have come out that utilize scene graphs to improve captioning. One common sort of pattern that we see emerging is one where on the process of converting the image to the caption, there's this induced scene graph layer in between that first converts your image into a scene graph representation, from which we can now then produce the caption. And what's nice about this induced layer is that once we produce a caption, we can reproduce the scene graph and create a cycle consistency sort of loss that allows to verify that the captions that we're generating are in fact consistent with the scene graphs that we're generating or extracting from these images. So it provides additional training signal and also provides this nice sort of structure and also allows people to even take subgraphs within the extracted scene graph and generate a variety of different kinds of captions that focus on different regions in the image. Now, another area that's been really exciting is thinking about how we can use scene graphs as a form of external knowledge when answering questions about images. So what we've seen people do very recently is take examples of images, convert and extract relationships from those images, and now utilizing those relationships as if you were given an external knowledge base about possible things that are going on in the image. And now you can reason over not just the raw pixels, but over this sort of extracted relationship set as well when answering questions. So now these kinds of models are using the question to attend over not just the pixels, but over this extracted relationships when answering the question. And finally, we've also been seeing a lot of examples of people utilizing scene graphs as a way of building creativity tools for generating images. So we can explicitly specify how different kinds of objects should be related to one another when we're generating an image. And this allows us to create enough sort of signals where the model can identify which regions of the image should contain what kind of object and what kind of relationships they should satisfy. And then we can now generate that image from that very specified input. So to wrap up, the community has been utilizing scene graphs for a wide variety of tasks. Ranging from, like I mentioned, image generation by first converting text into this structured scene graph. They've also been improving upon visual navigation and 3D understanding by using scene graph priors or even extending scene graphs to operate over entire 3D regions and rooms and houses, etc. We've also been seeing examples where scene graphs can be used to answer questions by using neurosymbolic methods on top of these graphical structures, very similar to some of the ideas that Aditya talked about earlier. And of course, we've started seeing examples in the HCI community where the scene graphs have been surprisingly really useful for creating creativity tools like sketching, where you can define what you want to be able to sketch, and then the model transforms it into a scene graph that then converts it into strokes. So to wrap up, what I've talked about today is scene graphs, which are this representation that's grounded in human cognition and how it can be used to design a variety of compositional models that can generalize very easily to novel compositions. And finally, we touched upon how scene graphs can be used for a variety of downstream tasks that are very core to computer vision and is a general purpose representation that is task agnostic. Okay, so thank you. That's all I have for today.
Thanks, Sanjay. These were really excellent presentations, both of them. Very thought-provoking, very transformational, I would say. So given that the audience has no questions, maybe we should start with our own questions. Naren, Mike, do you want to go first?
Sure. So Aditya, that was a great talk. And Ranjay, that was amazing. The first question, I have a bunch of questions for both of you. So first of all, are those relations that you generated via Mechanical Turk and all that, is it freely downloadable to the community, etc.?
Absolutely. Yeah. Okay. And I think, I can point you to, that's the URL. Where is it? It's the last one. Here you go. So if you just, so in GitHub, Elemental Cognition Glucose. So the entire data set is available. And I believe even the code for the crowdsourcing is available.
Okay, that's very good. And how does these rules compare to another comparable projects like maybe FrameNet, ConceptNet, the OpenMind?
Yeah, I mean, so they're all different. It's much richer than FrameNet, right? FrameNet doesn't really have rules as such. It has a library of these frames. And we actually have use FrameNet, but for a different purpose. It's like a dictionary. You map to relations, but there are no rules there as such. ConceptNet and Atomic are resources that are comparable. And that's why in the paper, we showed how Glucose maps to those. And Glucose just has a lot more knowledge compared to what's in there. And I think and we were inspired by Atomic. So we really liked the work that Atomic, the presenter, came to EC and gave a talk, Yejin, and we love that work. But there's one sort of issue that we had with it, which is that the rules were not contextual. You had a rule like, if a person puts their hand around someone, then they are happy. Well, that depends on the context, right? Like they may be upset as well, depending on the context. So we wanted to really ground these rules in a particular context. And we wanted to capture rules at two different levels, specific and general. So those are the two enhancements that we made over Atomic. But otherwise, conceptually, it's related to Atomic. It's just that we have a lot more data and they're grounded.
Okay, thank you. So we just got a question in this panel here. So let's read it. Can we enrich scene graph embeddings with Wikidata or some other domain-specific knowledge graphs? Did you all try scene graph for a specific domain?
Yeah, that's a great question. So yes and no, and it's yes and no because we're in the process of doing it. We've been recently thinking a lot about what are the different kinds of common sense knowledge bases that we want to tap into and start using and combining with the sort of graphical data that we have. So ideally, what we would want to be able to enable is computer vision models that can reason over not just what's happening in the scene, but also similarly reason over what might happen or what will happen. So instead of doing this from text, where you might already have this sort of structure built in, or even just words themselves, we're trying to do them directly from videos. So we're trying to build out benchmarks and also models where you can answer questions that are reasoning about the future or the past by looking at a chunk of a video as input. So it's still ongoing work. We're trying to actually use Atomic as the framework, but I should look into Glucose too.
Thank you. And there's one more question that just popped up. How do you capture emotion in the scene graph embedding?
Yeah, that's a funny question because we were worried about similar sort of things where coming up with a vocabulary of relationships or attributes is really difficult. And so whenever you're coming up with any of these vocabularies, you're automatically restricting the utility of the kinds of things that you're collecting. And so what we ended up doing was a compromise where we allowed people to talk about anything at all they wanted to in an image, and then we extracted what they were talking about into these graphical representations. So we do have people talking about emotions and what people are feeling. So in some cases, we do have data about subjective inferences about people's emotional states, even animals' emotional states. We have quite a few cats described as dumb, for example, in our data set. Surprisingly, dogs are never described as dumb, but cats are. I wonder if there's some expectation that we have that's higher for cats. But anyway, there are a lot of emotional sort of data available as well. We haven't really seen people utilize that data as much as we've seen people utilize the more sort of spatial and verb-like relationships in the data set. But it is available. We just haven't seen people use it.
So I have a architectural question for both of you. Like listening through your presentations, one thing kind of that struck me was that, okay, we are taking these rules and then we are using them to train these black boxes. And then we are evaluating the results of these black boxes. Is that really serving the purpose? Because we don't know what the black box is actually learning, right? Even though we fed it the rules and it produced better result, but we're not sure whether it actually learned those rules or it learned something else, right? So, and I think the architectural question here is, I think if you're building an AI system, what should sit at the top? Should it be sort of some kind of a rule-based knowledge graph model, which is calling the black box, or a black box which is using rules as input to learn what it is doing, right?
Yeah, that's a good question. And the way we see it, I think it's an empirical question: which system will work better? One that is symbolic at its core, and has neural functions plugging in. That's the approach that we've taken with Braid, right? Or lots of other people have taken approaches where it's a neural system at its core, end-to-end neural, but then you might plug in some logic or some symbolic technique. Maybe they're expressed as constraints during decoding and stuff like that. Um, honestly, I don't know which one will work. I think both parts are, from a scientific standpoint, we should explore both. The reason we like ours is because it's more easily debuggable. It's more interpretable because it's fully transparent. You can see what the explanation is, and these statistical functions, you can get data for them in a very clean and separate way. You can you can get data. Like if I go back to, can I share again one thing I can show you? Is one interesting aspect of this design is, how do we use this? Like we might show an explanation to the user, right? And now the user might come and tell us, well, this explanation is wrong. This rule doesn't make sense in this context. Or this fact is incorrect. Your NLP that extracted this fact from the text was an error in the semantic parsing. So we can get that fine-grained feedback from the user on elements of the explanation. And that feedback becomes training data to improve those statistical models, right? So you can independently improve your semantic parser based on that feedback, or improve your rule generation, your dynamic rule generation model based on the rule feedback. And they can do that because we're exposing the full explanation on them. Because of the way we've designed it, where the neural ones help. And So
Ranjay, do you have a take on this?
I don't know if I could answer that any better. That's exactly my take as well. What we're trying to do is induce these sort of constraints where we can now go in and evaluate whether the model is able to sort of satisfy the constraints that we've set. And what's nice about these constraints is that we are moving away from these black box models completely in a lot of my work, and we are trying to sort of build in these individual components that are all plugged together to produce your final output. And so when there's an error in any of these individual modules, we know where the error came from, and we can sort of fix those errors, just like the example that I just provided. The other thing that we can do by having this sort of structured representation is that even if we decide that, okay, we don't want to have models like this, we just want a simple black box end-to-end model, well, we can now test those models at the very least using these sort of structures that we built out, because we can use those structures as benchmark data to make sure that even if our models themselves are uninterpretable, they should still be able to generalize to novel compositions or more compositional steps of reasoning, or any of these other kinds of characteristics that we might care about in our model.
Okay. Here's another sort of high-level question for both of you as to, in the process of doing this work, have you developed or come across principles for designing a good knowledge graph? So as a concrete example, Ranjay, in your presentation, you were showing a person holding an object, right? And you had holding as a relation, right? And I've worked on knowledge graphs for a long time, and I'm like, well, why is holding a relationship? It's not a relationship. It should be an event, and the person should be a participant in that event. But again, I don't have any basis to criticize your knowledge graph saying that, oh, this is not good. But there is the question of how do we decide what's a good knowledge graph?
Yeah, let me criticize some of my work. It's really confusing sometimes to come up with the right knowledge representation. When we were designing our scene graphs for Visual Genome, we took a very task agnostic approach where we allowed people to sort of annotate anything for us, and then we extracted the relationships from there. So it led to two interesting phenomena. First, it led to representations that were generally useful for a variety of different kinds of tasks. And that was useful because now people can use these scene graphs for different tasks. But at the same time, it's not clear if they were really going to push state of the art in any one of these specific tasks, because they weren't designed for a given task. So when we designed Action Genome, which is more focused on just action detection, we designed that one to be more task specific. So we didn't annotate every single relationship. We only annotated those ones which we knew were very, very important for the kinds of events that we wanted to detect. And we found that to work really well and really lead to much further improvements for that task. But the downside is now that representation is not as general, and so isn't as useful outside of the action detection kind of setup. So there are two competing sort of directions here. Do you make these representations more general, or do you make them more task specific? I don't really know where I stand at the moment. I think this is why we're sort of experimenting and trying to figure out. But if you are trying to maximize performance in something, building representations by thinking deeply about what makes it task specific and what is really important for that task is a better one. So holding might not be one that's important for you if you don't care about it.
Okay, Aditya, you have a take on this?
I mean, it's a good question. My sense is there's no such thing as a perfect knowledge representation. You're never going to get it right. They did different perspectives that a modeler may have. And like I said, I started off in the KR&R community many years back, right? Mainly working on the reasoning side, not so much on the representation side. Part of it was precisely this: like, if you went to a very narrow domain, you could spend time thinking through a clean, formally valid, precise logical model. But when you come to natural language and natural language understanding, it's very hard to get that, because it's just inherently very messy and ambiguous. These terms, these concepts, these relationships, you and I may have very different meanings in our head for the same word, right? For the same term. And so coming up with a clean, well-defined ontology of concepts for language, I think is intractable. And so whatever solution our philosophy has been, whatever solution we have devised, it has to be flexible in its KR. It has to be able to, we worry less about the actual KR and more about the algorithms that do the reasoning, that they should allow for fuzzy matching and they should allow for variations in representations. I mean, that's just my take.
Okay, no, that's fair enough. Looks like we have another audience question.
Yes. What considerations are you taking to reduce the bias in the scene graph recognition? It's a question for Ranjay.
That is a good question. So we've done a few things in the past. So there's a lot of bias because some relationships are just a lot more common than others. What we've typically done is we've added a variety of regularization and training tricks to make that better. But we've also added language constraints where we would extract these similar kinds of relationships from language data and also give higher weight to things that we've seen people talk about on language benchmarks that are out there. So those are methods that we've tried to reduce biases. They've typically worked and allowed us to sort of predict things that were new or novel, but it's still not at a point where we aren't completely unbiased. There is definitely a lot of noise from the data set or biases from the data set that sort of seeps into our model's predictions. So it's still an active area of research. We've typically only used, like I said, training tricks or language as an additional source of data.
Sounds good. In some way, your work does fundamentally address this bias reduction problem, right?
Yes. Yeah. So in a sense, we're explicitly trying to reduce the bias because we're breaking things up into its individual components. Yeah. But again, even so, there's still quite a lot that does seep in because, as you can imagine, the model sees a person and just assumes that the person would be doing these activities and not others just because they're more likely. So we do try to take additional approaches to improve it.
So we've got about a minute left. Maybe each of you can give us your vision for what's next for you in like 30 seconds each, and then that'll be a good way to wrap up today's session. Aditya, you want to go first? You're muted.
Sorry. Yeah. So, we haven't solved natural language understanding by any means. I think all we've shown is that there is a new recipe for doing NLU reasoning where you can combine neural transformer-based models. It doesn't have to be transformer, but neural functions that are trained on knowledge to produce rules, and then combine that with a symbolic reasoning engine for doing scalable reasoning. And I think there's still many challenges left. Like one of the things we want to do is combine text with image and do question answering on visual data sets, which relates a little bit to the work that you talked about. And then there are lots of open questions about, we still haven't, the models work well in some domains. We still have the domain adaptation problem, and transferring knowledge from one domain to the other. and showing that we can learn efficiently with very little data. So one of the things we did is we collected 600,000 rules in glucose. Did we need so many? Like we still have to do experiments to see, can we train better models that can learn with much fewer data? So I think we took, in some sense, the easy way out by just fine tuning, T5 or GPT-2, right? These are existing architectures. For me personally, I think coming up with novel models that can learn more efficiently on logic and symbolic data is very interesting.
Okay. Ranjay?
Yeah, there's quite a few different directions. I am interested in one, really diving deep into compositional spatiotemporal sort of representations and reasoning problems, combining them with common sense knowledge bases. I'm also interested in active agents that are actively pursuing different kinds of actions and how that leads to different changes in the world because of their own actions. I'm also interested in a lot of multi-agent kind of frameworks and how these representations might be different depending on how much each agent has individually observed and how they can share that information to do collaborative kind of tasks. So that's sort of where my research is headed towards.
That's great. That sounds awesome. Sounds very exciting, very fascinating. Frontier of AI. We are pretty much at the end of our class time. So I'd like to thank both of you for taking your time out and sharing with us your work. And it was really a fascinating session, and we hope to stay in touch with you to track what's the next frontier you advance. As far as our class is concerned, we will continue next Tuesday, and our theme for next week is on how do we do inference with knowledge graphs. So thank you all very much, and we'll see you next week.
Thank you.
Thank you.
Thank you for having us.
Thank you.
Bye.